airways with smooth muscle that's keeping them open, or if the smooth muscle contracts too much, closing them down. Beginning of the respiratory system occurs where the first alveoli appear. So these, although they're still airways, they're now respiratory, bronchioles, and gas exchange can occur. Here we've got alveolar ducts, because there's still some wall space, but now we've got more alveoli. And it will end in what's called an alveolar sac, which is just alveoli everywhere, simple squamous cells with the surfactant secreting cells in the partition. And then each alveolus connected either to the duct system through the sac or an adjacent alveolus. So remember that each alveolus, all the alveoli in a sac are usually interconnected. So if one has an increase in pressure for some reason, it will just squeeze all its air out into another one that has lower pressure. So our lungs, in order to keep all our alveoli open, we have to have equal pressure in every single alveolus. And not all alveoli are made the same. We've got a big alveolus here and a small alveolus there. So the fact that you have bigger volume should mean you have lower pressure. Smaller volume should mean we have higher pressure. But surfactant equalizes the pressure in the alveoli so that small and large alveoli have the same pressure. So they both stay open. Nobody's shoving their air into their neighbor and closing down. They would do that if they had a higher pressure, as gradients go from high to low. So high pressure to low pressure, and the high pressure then would alveolus would close down with no air in it. You lose surface area for gas exchange. So surfactant will take the inequity of the size of the alveolus and even the playing field. So every single alveolus, no matter what its size, will have equal pressure. We'll be going over that again with the slides. So that's an introduction.
Air usually is drawn in through the nose into the nasal cavity. Here, secretions warm and moisten it. From the nasal cavity, air enters the pharynx or throat. The pharynx is the entrance to the larynx. Paired vocal cords in the larynx vibrate as air passes by, making speech possible. The epiglottis is a tissue flap at the entrance to the larynx. When you swallow, it folds over to direct food into the esophagus. When you breathe, it points upward and air flows through the larynx and into the trachea. The trachea carries air to the lungs. The lungs lie in the thoracic cavity, to the left and right of the heart, and above the diaphragm. A sac-like pleural membrane lies between the outer surface of the lungs and the inner surface of the thoracic cavity's wall. Contractions of the diaphragm and intercostal muscles between the ribs change the volume of the thoracic cavity and ventilate the lungs. Inside each lung, air moves through finer and finer branchings of a bronchial tree. The smallest bronchioles lead to alveolar ducts, which end in cup-shaped alveoli. Each alveolus is associated with pulmonary capillaries. Driven by its partial pressure gradients, oxygen diffuses from alveolar air spaces into lung capillaries. Carbon dioxide diffuses in the opposite direction. Now let's check what you have learned. Drag the text to identify each structure.
So nasal cavity should be by the nose, where the hole is, should be here. This is shared space in the back of the throat, so it should be pharynx. This is going to close off your respiratory system during swallowing. That's your epiglottis, epi on top of the two slit membranes that form, not slit membranes, but two membranes that have a slit in the center that forms your glottis. So this is on top of the vocal cord, which is your glottis. Esophagus, which has nothing to do with respiration. And then larynx, which is your voice box.
That's correct. When you are breathing normally, air enters through the nasal cavity, passes through the pharynx, past the epiglottis, and into the larynx. When you swallow, the epiglottis tilts downward to direct food from the pharynx into the esophagus. Drag the text to identify each structure.
Diaphragm. And you've got trachea. Do the easy ones first. Pleural membrane. It isn't that other one, so it's got to be this one. And this is between ribs, muscle, so that one.
That's correct. The trachea is a tubular airway to the lungs. Each is surrounded by a pleural membrane. Contractions of the diaphragm and intercostal muscles increase the size of the chest cavity during inhalation.
Okay, so bronchioles. All the airways up to the bronchioles are going to have cartilage pieces in their walls, and that will help to keep them open. So when the cartilage plates run together, you can't get that airway any smaller. The bronchioles are the only ones that are relying on the tethering effect, and they're going to be strongly influenced by any chemicals that are down there. So any irritants like histamine, you're going to have airway constriction. You're going to have, if you have a decrease in CO2, bronchioles constrict. Increase in CO2, dilate the bronchioles. So even at the level of the lungs, CO2 is driving how much air is getting in and out of your lungs. And then hormone-wise, you have your epinephrine. Sympathetic nerves, bronchodilate. And the epinephrine, which binds to the norepinephrine receptor, bronchodilates. Get increased air in and out. So here we've got our alveolus again. We've got our septal cells. They look like this. They kind of look like they're hanging on to the edge or in the membrane. So I don't know about that. But anyway, you have them secreting a surfactant, which then will diffuse and cover the surface of the alveolus. So I like that picture because they've given the surfactant a color. It's thicker over the type 2 alveolar cell or surfactant secreting cells, and then it diffuses away and coats the rest of the surface area. And that will then push water molecules apart and interfere with their interaction with each other. That will keep these alveoli open. It will also keep the pressure in this alveolus, which is bigger than that, although we can't see it all, but let's say these two are smaller alveoli. If this was a bigger alveolus and these were smaller, by the true laws of physics, they would have higher pressure since their volume is smaller. And they would then empty into the lower pressure area where the volume is bigger. So these would close down, and this one would be the only one with gas in it. So that would mean that the only place for gas exchange now is this surface area and that surface area. If you can keep all the alveoli open, although you can't see the other capillaries, there are other capillaries here and here, and so you have more surface area for gas exchange if you can keep more alveoli open. Type 1 pneumocyte and your endothelial cell of your capillary, you have a 0.5 micrometer distance between the plasma in your capillary and the air in your alveolus. So we're not physically including surfactant in the diffusion distance, but it is there and it is part of the diffusion barrier. So the diffusion barrier is surfactant, type 1 pneumocyte, shared basement membrane, and endothelial cell of the capillary. Alveolar macrophages, they'll be keeping everything clean and also getting rid of old surfactant so it doesn't clog up your alveoli. This is kind of a funky picture. They put the resin into the alveoli and then they put resin into the blood vessels and the capillaries so that you can see the interconnection between the surface. Well, this one has been, the capillaries have been cut away, but that's an alveolus. And here's an alveolus with the capillaries right on top of it. So a lot of capillaries per individual alveolus for purpose of gas exchange. Another way to look at it, this is a scanning EM. I'm not sure why they colored it red. It shows you the red blood cells, they're in black, are in the capillaries going through at a pace which will be optimum for the gas exchange. If you have low O2 concentrations here, you're going to slow the transit time of your red blood cells down so you have time to get the few oxygen molecules to the red blood cell, to the hemoglobin. If you have a lot of O2 here, you can speed up the transit time of the red blood cell because you have a lot of oxygen that will be diffusing across and you'll still get enough oxygen loaded on the hemoglobin. So here we've got precapillary sphincters again. You come back to this picture here, oops, wrong direction. We're going to have precapillary sphincters here, not to open up or close down capillary beds, but to alter the transit time of red blood cells through those capillaries. If your oxygen concentration in your inhaled air is going down, then you want more time to get those few oxygens to the red blood cell. So you slow the time the red blood cell takes, increase the time, you slow the transit time from the beginning of the capillary to the end by constricting the precapillary sphincter. Slow the amount of blood entering. That will decrease the time that the red blood cell, will decrease the transit time. It will increase the time that the red blood cell spends at each little section of the capillary, offering more time to the oxygen molecules to get onto the hemoglobin. If there is adequate oxygen there, keep the precapillary sphincters open, red blood cells go past very quickly, but O2 loads down its concentration gradient. There's a lot of it in the alveolus, so it's diffusing across quite quickly, adequate time for loading of the red blood cell. So a lot of capillaries you can see in the surface for this alveolus and that alveolus and that alveolus.
The alveolus is the functional unit of respiratory exchange. This is a cutaway view of one alveolus. The air in an alveolus is separated from the blood in a pulmonary capillary by a thin, three-layer respiratory membrane. The respiratory membrane consists of the capillary epithelium, the alveolar epithelium, and a fused-together basement membrane that supports both epithelia. Oxygen and carbon dioxide diffuse easily across this membrane in response to their partial pressure gradients.
Okay. And surfactant. So don't get surfactant. And then video.
So what exactly do they do? These are actually pig's lungs.
I did the same size as what my lungs would be.
They're pretty similar. They might actually be a bit bigger. What we can do is actually inflate them. If you push that red button just there, they should blow up.
Oh my god!
Yeah, keep it pressed in, keep it pressed in. Then, okay, stop now, stop there. When we breathe in, the air travels down the trachea, then off into each lung. From there, it goes down smaller and smaller tubes, like the branches and twigs on a tree. Keeping these tubes clear is crucial. If they get blocked, we become susceptible to infection and can starve our bodies of oxygen. And then because they're elastic, they want to deflate. Surprisingly, perhaps, it's our body's need to breathe out carbon dioxide which drives our lung function. Breathing in oxygen is the other side of the equation. Inside the lungs, the oxygen passes into the bloodstream, where it's carried off to all the cells of our body. Without oxygen, every life-sustaining process would shut down. So much for the theory. Time for Lisa to get hands-on, starting with the large airway that branches off into each lung, the bronchus. And the bronchus has got cartilage in its walls. Have a feel of that. You should be able to feel the cartilage there, the gristle. Yeah?
It's like your ears.
It is. It's just like it's the same sort of cartilage, absolutely. And the reason there's cartilage in the airway is
there. It's not the same. What's the difference? What kind of cartilage you got here? Elastic. What you got in your bronchus? And good. Oops. I just screwed that up. Okay, you can watch it again.
So what exactly do they do? These are actually pig's lungs.
I did the same size as what my lungs would be.
They're pretty similar. From there, infection and can starve our bodies of oxygen. And then because they're elastic, they want to deflate. Surprisingly, perhaps, it's our body's need to breathe out carbon dioxide which drives our lung function. Breathing in oxygen is the other side of the equation. Inside the lungs, the oxygen passes into the bloodstream, where it's carried off to all the cells of our body. Without oxygen, every life-sustaining process would shut down. So much for the theory. Time for Lisa to get hands-on, starting with the large airway that branches off into each lung, the bronchus. And the bronchus has got cartilage in its walls. Have a feel of that. You should be able to feel the cartilage there, the gristle. Yeah?
It's like your ears.
It is. It's just like it's the same sort of cartilage, absolutely. And the reason there's cartilage in the airway is to hold it open and to stop it collapsing down. You can also see another tube there. You can see that that's an artery. So that artery is bringing blood away from the heart into the lung, and in fact that artery is carrying deoxygenated blood into the lung, ready to pick up oxygen, and then the oxygenated blood comes back through veins, which are a bit difficult to see because they're so thin-walled. I've talked Lisa through the basics, but she already knows the very first thing she should do for her lungs.
Stop smoking.
Stop smoking, yes. Okay, why did the girl have to press a button to
what exactly do they do? These are actually pig's lungs.
Are they the same size as what my lungs would be?
They're pretty similar. They might actually be a bit bigger. What we can do is actually inflate them. If you push that red button just there, they should blow up.
Oh my God.
Yeah, keep it pressed in, keep it pressed in.
Oh my-
Okay, stop there, stop there. When we breathe in, the air travels down the trachea, then off into each lung. From there, it goes down small.
You have to physically press a button, and the lady said, keep pressing, because the lungs were not completely inflated. And then she says, knock. So that also we just talked about. And then they deflate. When they deflate, are they going to the size that they normally would be inside the pig? Larger or smaller? Smaller. Why? There's no attachment of the pleura anymore to the parietal pleura, which is attached to the chest wall. So the lungs don't have that tethering effect. To inflate the lungs, you actually have to work against the water pressure in the lungs. These have been outside the lungs the body long enough that they're not going to have their complete surfactant complement. Plus, when the alveoli do really collapse due to the fact that there's no tethering to the chest wall, even the surfactant can't keep the alveolus open. The alveolus will collapse. Then water molecules are attached to each other. And then you have to have positive pressure. You have to have that button, or you have to blow to try and get those alveoli to pop open. A person whose lungs collapse, you ever heard of a pneumothorax? There was a guy who got stabbed up Coco Head and his lung collapsed. He could not inflate his lung for himself. You have to, first of all, close up the hole that allowed the air to get into that pleural cavity, which caused the lung to collapse. And then you got to use positive pressure to blow the lung up and get it reattached to the chest wall again. So it's a valuable learning lesson. You take the lungs out or introduce air into the pleural cavity, same thing happens, lungs collapse. So here they took the lungs out of the pig, the lungs collapsed. Had to use positive pressure to blow them back up. Clamp them, the air will stay in. So you saw she had a hemostat, she had the trachea clamp, the air stayed in the lungs. And as soon as she released the hemostat, then the air came out and the lungs collapsed again. So the elasticity of the lung is very important for the respiratory mechanics. The elasticity of the lung is going to allow the lungs to follow the chest wall out, but it's also going to create tension that will want to pull the chest wall back in. And so if you use your respiratory muscles to expand the chest wall, with this elastic recoil that wants to bring the chest wall back in, you turn off your respiratory muscles, then the elastic recoil will bring your chest wall back. And that's what you're doing right now when you're quietly breathing. You fire from your brainstem to the phrenic nerve to your diaphragm, or the sympathetic nerves to your intercostals. Your rib cage goes out, your diaphragm goes down, you breathe in, then you turn off the stimulation, and they go back to their resting length. Why do they go back to their resting length? Because of the elasticity of the lung. It wants to shorten again. So we're going to be talking about this fight between the chest wall and the lungs. the normal shape of your chest right now is due to that fight between the elasticity of the lung that wants everything to collapse and the chest wall, which actually wants to go out with the respiratory muscles and actually would be a little bit bigger if the lung collapsed. And that's how the people at the emergency room knew that the guy who got stabbed, that actually his lung had collapsed. Because when he came in, one side of his chest was bigger than the other side. When the lung collapses, it's detached. It's no longer pulling the chest wall in, so the chest wall gets a little bit bigger on that side. Plus, there's the air pressure as well in the thoracic cavity. The normal tug of war between the chest wall and the surface of the lung keeps a negative pressure in that pleural space. And that also is going to help with our respiratory mechanics. But elasticity is important. They say, think of getting a lollipop and shoving it into a water balloon. Now, it's not the same consistency at all of the tissue, but the effect is you're taking a structure that is round, or a lot of 3 million of these little round things on a bronchial stick, and you're shoving it into a water balloon, which is then going to cover the surface of all your little round things, your lollipop, which will be your visceral pleura. And then you're going to have that water space that's going to be your pleural cavity, and then this outer surface of the water balloon, which will actually be attached to your chest wall. So that's their analogy for the relationship between the lungs and the pleura and the pleural cavity. Yeah.
This is something for the heart rate.
Yeah. So your fist shoves into a water balloon there. I guess they didn't want to use the fist analogy and confuse you again,
Yeah.
so they decided they're going to use a lollipop instead.
The heart is long and the ball is 6 and 3.
Mm-hmm.
So it's like you have pleural cavity, long, so you have the heart rate.
Yeah, so same principle. You have lungs with a pleural membrane instead of pericardial membrane or epicardium, and then water-filled space with other stuff, and then a parietal, in this case pleura, the other case it's parietal pericardium. Yeah. Yeah. So you got now a double lollipop. You got your left and right lungs on your tracheobronchial stick. They have been pushed into your water balloons, which are your pleural membranes, and you got your parietal pleura stuck to the chest wall and the diaphragm, and the mediastinal structures, and then the visceral stuck to the surface of the lung. And then the water in between is watery enough so that the water molecules actually attract each other, negative to positive, hydrogen to oxygen, and that creates enough tension that the membranes actually stick together, so that the chest wall movement or the lung elastic recoil will help to change the volume of the lungs. When the chest wall muscles turn on, the volume goes up. When you turn them off, they will go back to their resting length, but also the elastic lung will go back to its resting volume, and air will come out of your lungs. So this space here is called intrapleural. It's between the pleura. There's also a term called intraalveolar and intrapulmonary. Intraalveolar is different enough from intrapleural that you're not going to confuse those terms, but intrapulmonary and intrapleural, I find students tend to get confused with those two, and therefore pressures which are extremely different in those two areas, they get the pressures confused. Intrapleural is between the visceral and parietal pleural. That's going to be a negative pressure, maybe negative 3, 4, or 5 millimeters of mercury. Intrapulmonary pressure is going to be pretty high. It's either going to be higher than atmospheric or just lower than atmospheric, but around, at sea level, around 760 millimeters of mercury. So 760 versus -4, big difference. You can't get those confused now or later. So pressures. We have atmospheric pressure at sea level where we are now, it's 760. Even when the barometric pressure goes up with a storm coming in, it doesn't go up very much. It might go up to 762, but probably not much higher than that, even with a real nasty storm coming in. And when the barometric pressure goes down with the low pressure system that comes in, it doesn't go down too much, usually around 759. Hardly ever gets to 758. So it's around, for our purposes, we're going to say it's 760 all the time. That's atmospheric pressure. When you write it, then it's big P and then ATM here for atmospheric. You can ask me on the test. I will tell you what the little letters stand for. Intraalveolar pressure, they don't use anything but an A, so P sub A. Sometimes they'll put P sub ALV. So you can, it might appear in a textbook for intraalveolar pressure. It varies with ventilation. If your chest wall is relaxed and your diaphragm is relaxed, then you're at resting lung volume. If your glottis is open, then you will equilibrate intraalveolar pressure with atmospheric pressure. So if your diaphragm and your external intercostals are relaxed, and you've got a glottis that's open, then these two are equal. This will be 760, this will be 760. Units, millimeters of mercury. So all of these little alveoli and the airways will be at 760 millimeters of mercury. If you then inhale and the volume goes up, what's going to happen to alveolar pressure? Okay, Boyle's law says P1 is equal to P2 V2. So if you start at resting volume and pressure 760, and you inhale, so volume 2 is going up, so it's greater than V1, then what's going to happen to P2? Has to go down, otherwise the two sides will not be equal. To solve for what P2 is, then you just rearrange the equation. P1 V1 divided by V2 will give you P2. Okay, so no Boyle's law, know how it affects the change in pressures or volume. If you breathe out and volume goes down, what happens to pressure? Goes up. Okay. So it's going to be less than, greater than, or equal to 760 with ventilation. Intrapleural pressure, also called intrathoracic pressure, is the pressure that is between these two pleural membranes. So in the pleural cavity, this is IP pressure, intrapleural. Since there's a tug of war going on here, the elastic lung wants to go this way and the chest wall wants to go that way. That is creating a negative pressure in that intrapleural space, and it usually is around -3 to -4. I've seen some books say -5, but I haven't seen anything say less than -3. So it's going to be negative, and it's going to be way less than atmospheric pressure. So here we've got our lollipop, and our airway is the lollipop stick. It's been pushed into our water balloon. We've got intrapleural space here, that is our pleural sac, our pleural cavity. We've got a thoracic wall out here in beige, where our parietal pleura is attached. And we've got our lung here, which is our lollipop, where our visceral pleura is attached. As long as our glottis is open in our larynx, then atmospheric and alveolar pressure are going to be equal. They're going to be 760 millimeters of mercury. So caveat is chest wall relaxed, diaphragm relaxed, so you're at resting lung volume, and your glottis has to be open. And then you have equilibration with atmospheric pressure. The intrapleural space is going to be around -3 to -4, your book is saying, so fine. And then some others will go up to -5, but not lower than -3. So usually what is happening, you can put a pressure sensor into that intrapleural space and measure the fluid pressure there, and they come up with a pressure of 756. And then when you look at the difference between what is outside and 756, it's 756 minus 760, so just math, but you're going to end up with a negative number because you're starting with this being lower than what's out here. That's where you end up getting this -4 millimeters of mercury. And that usually is what they talk about, and the book will continue talking about this space being at -4 millimeters of mercury. They won't continue talking about it beyond this point as being 756.